is Dalit, and I'm a postdoc at the Physics of Fluids group at the University of Trenton. And today I'm going to talk about how you can use small amounts of polymer additives to equisyncs in order to suppress satellite droplet formation. And this is a work that we have done in close collaboration with Canon production printer. So why satellites, or rather why not? For inkjet printing, you can see, as shown in the figure here, sometimes with the primary droplet we get these satellite droplets. Now these satellite droplets are traveling at a different velocity than the primary droplet, so they reach the substrate at different times, resulting in irreproducible printing, such as these non-sharp corners, smeared edges. So essentially that means that satellite droplets equals poor print quality. So our goal going forward in the talk are twofold. One, can dilute polymer suppress satellite droplets? And if you've read the title of my talk, you already know the answer, or you can at least guess it. It's yes. But number two is, what is the physical mechanism for such suppression? Now we'll take a look at the experimental setup. So we have a printhead. It's a piezoacoustically driven printhead. And the nozzle diameter is 50 micron. We look at it through a microscope connected with a high-speed camera. The pulse that is being sent to the printhead is of the trapezoidal nature, where we vary the maximum voltage amplitude, VMX, and the pulse width, TW. And for water, this is how the jetting looks like at 50 volts. And you can see that a nice clean single droplet is being formed without any satellites. But if I just bump up the voltage to 60 volts, you can see that a satellite is being formed. And this is something that we do not want. So the question is, can polymer additives suppress satellites? So we're going to try that. So again, this is how satellite formation with water looks like. But if I add very small quantity, 0.003% of polyethylene oxide, a million molecular mass, you can see that we don't see any satellite. Instead, it forms a long filament, the large head droplet, a very thin tail, and a small tail droplet. And the tail droplet is pulled into the head droplet, resulting in a single droplet without any satellite. So this happens because these polymers impart viscoelasticity to the solution. So now, in addition to capillarity pulling the tail or forcing the tail to contract, there's also viscoelasticity in it, which basically is helping capillarity to pull the tail into the head droplet here, thus resulting in no satellites. But if I increase the polymer concentration to 0.009%, which is also not that much of an increase, you can see that there is no jetting at all. Instead, a filament comes out, it doesn't separate from the nozzle, it goes directly back up. This is something we're going to refer to as retraction going forward into the talk, but it's also referred to as the bungee jumper in literature. So this suggests that there is an optimum concentration range for suppression of satellite droplets, and it's imperative that we find that out. So now for the driving conditions, we are actually varying two quantities in our experiment, the pulse width and the pulse amplitude, and we need a single quantity that represents the effect of those two quantities. So for that, we look at the meniscus motion inside the nozzle. It's a glass capillary, so that allows us to do that. So here we're looking at the meniscus motion inside the nozzle. So this is our tapered nozzle, and the thing that is moving inside is basically a liquid. The printhead is operated in the pull push mode. So what happens is we basically pull the liquid meniscus up and then push it down, and that creates our filament. The videos are for 3 different concentrations at the same driving conditions. And you can see that qualitatively you can't really make out a difference. But what happens quantitatively? So for that, we measure this Zm, the meniscus position inside the nozzle in its time, and I plot it for 3 different conditions, 3 different concentrations at the same driving conditions. And I ask you to focus on this maximum meniscus position Zm max. And you can see that there's not much of a difference or any difference at all between the 3 concentrations. It's just that Zm max is independent of polymer concentration. So we define our phase space in this way. Here on the horizontal axis, we have the nozzle Deborah number described in this way, where lambda is my relaxation time. So the nozzle Deborah number is an indication of the concentration of the solution. And Zm tilde on the vertical axis represents our driving condition, where it is expressed as Zm max normalized by the nozzle diameter. And for the retraction of the bungee jumper, it happens at high concentrations and at low driving. And now when you increase the driving, there is finally jetting and it goes into the no satellite regime. This is again the regime that we want. But if we increase the driving a bit more, then it goes into the satellite regime again, something that we don't want. So now we can basically delineate how our three operation regimes are. And going forward, we are just going to focus on this green no satellite regime, which is basically our regime of interest. So now, again, focusing on the no satellite regime. If you remember, in the no satellite regime, we form a very large filament with a large head droplet, a small tail droplet, and a filament connecting it. And as the filament is falling in the downward direction, the tail is being pulled closer to the head, and at some point they coalesce. So we measured this distance, L, against time for the cases where there are no satellites, and I show them for different driving conditions and different concentrations. So the two data points, the black two data sets, black and the red one here at the bottom, are for Newtonian liquids, and the rest are for viscoelastic liquids. And two conclusions directly jump out at us from this plot. One is the contraction length, L, it decreases linearly. Well, this is something that you expect for Newtonian liquids, but for viscoelastic liquids, it's unknown, and it's something new that we see from these experiments. Also, the velocity of contraction, which is the slope of these lines, it's higher for the viscoelastic case. For the Newtonian case, it's well defined, it's the telekinetic velocity. So that indicates that the viscoelasticity plays a role in the telekinetic-like velocity for these viscoelastic filament retraction. So we construct a very simplified model to try to explain these observations. But first, let's recap the contraction process again. As shown in this video, so again, we form a long filament with a large head droplet, a very small tail droplet. And as it falls, you can see that the head droplet size really doesn't change. What happens is the length of the tail decreases as the tail droplet is being pulled towards the head droplet. So our geometry for the model looks like this. We start out with a large head droplet and a long cylindrical tail at initial time. Its shape is given by this dashed line, but as it starts to contract, this tip basically moves in the negative z direction and starts to form a spherical bulb, which we call in our experiments the tail droplet. Our control volume is this red dashed box here. And within the control volume, the balance of forces is that the rate of change of momentum is balanced by the surface tension and the elastic tension. So if you write down the equations in the slender jet framework, this is the continuity equation, this is the momentum equation, where this is the capillarity contribution, this is the stress due to viscosity, and this is the viscoelastic contribution for an all-rod B fluid, where AZZ and ARR are the components of the conformation tensor A defined in this way, where X basically denotes the length of the polymer itself. Here, the polymers are modeled as two beads connected by a spring. So if you write down the rate of change of momentum, the expressions for them, so essentially what happens during the retraction is there is some fluid moving into the tail as the tail droplet, essentially, as the tail is retracting. So the rate of change of momentum for that fluid moving into that is given by this expression. And from the equations that I showed you in the previous slide, we can also get a rate of change of momentum expressed in this way. And now if we equate them, dLdt, which is my contraction velocity, can be expressed in this form, where the negative sign indicates motion in the negative z direction as shown in the figure. Here, this is the Newtonian contribution. This is identical to the telekinetic velocity, and this is our viscoelastic contribution. Now we can simplify this expression a bit further, because since this is an elongational flow or very strong extensional flow, we can basically neglect ARR as compared to ACC. And this expression can be simplified to this, where This quantity is always positive, which means that our contraction velocity is increased by viscoelasticity as compared to the Newtonian telegraphic prediction. So now we simplify it further. We write down the constitutive equation. One of the assumptions during the derivation of the rate of change of momentum was within our contour volume, V and dV dz, so velocity and the gradient of velocity are zero. So if we use that in the constitutive equation of ACZ again, we find this Maxwellian decay where A0 denotes the value of ACZ at C equals to 0 and T equals to 0. So basically, the initial ACC value at the origin of our coordinate system. Again, I must clarify that this is a coordinate system that is moving with the fluid itself. So it's co-moving with the filament. So within our coordinate system, our filament is at rest, and our entire filament is at rest. So this is our final expression of the retraction velocity. Now, if I plot this against time, if I integrate this and plot this against time, I can get a variation of the length with time. So I plot here the non-dimensional values of those, where length is non-dimensionalized by the radius r0 and t is non-dimensionalized by the capillary time. And this line basically denotes the variation of the length with time for a Deborah number of 10. Deborah number is defined as polymer relaxation time over the capillary time, and A0 of 10. And you can see that although there is an exponential here, for our range of experimental parameters, the variation or the decrease in length is linear. This is also something that we see from the experiments. Now, if I increase A0 while keeping Deborah number constant, you can see that the slope decreases. So it's a strong function of E0. But if I keep E0 constant and vary Deborah number, it doesn't change that much. So our contraction velocity is a stronger function of A0 and not Deborah number. But this A0 is not obtained a priori from our experiments. It's very difficult to determine. So what we can do is we can find A0 by fitting it to our experimental data. So again, this is the expression that we want to fit to our experimental data. And this is how the fit look like, where the discrete data points are from the experiments and the solid lines are the fitting. So now we have A0 values for all experimental data sets, but how can we relate it to the experiments and what physical meaning can we get out of it? So if we revisit A again, or A0 again, A is the conformation tensor defined in this way, and A0 is a component of it. So we can say that A0 is essentially related to the square of the instantaneous polymer length. Now our polymer length is related to its initial stretching. And we can also say that the aspect ratio, the initial aspect ratio of our entire filament itself is also related to the stretching of the filament. Now, we can assume that the polymer stretching and the filament stretching are equivalent in such a one unidirectional flow. And then we can combine these arguments to say that A0 should vary as the square of our filament initial aspect ratio. So can we get this kind of relationship from our experimental measurements? So here I plot L0 over R0, that's initial aspect ratio in the horizontal axis, and A0, which we obtained from fitting with our experimental measurements on the vertical axis. And you can see that the data points fall very much on the straight line. I mean, the agreement is reasonable. There are some deviations, but that's also because we don't take into account several other factors that might be happening, such as wetting effects, non-axisymmetric effects, and also polydispersity of the polymers itself. It's also important to note that the A0 that we find here is of the similar order as the one predicted by Lender et al. In one of their earlier works. So to conclude, we can say that viscoelasticity can result in the suppression of satellite droplets. We identify a regime map. We show that the length of the contracting filament decreases linearly with time. We show that this contraction velocity is higher than the Newtonian telegraphic prediction. And we devise a very simple theoretical model that predicts our experimentally observed behavior. Thank you for your attention. And if you have any questions, please feel free to reach out to me. See you later.